Hello, everyone. Good afternoon, good morning, good evening. My name is Carmen Guguta, your host from Technobis Crystallization Systems. Today's webinar is brought to you by our application specialist, Jyoti Yadav. And the webinar is Unlocking the Power of Solvent Selection, Influence of Solubility, Nucleation, and Crystal Habit of Ascorbic Acid. Today, you'll have the chance to hear more what you can do with our instruments, the Crystal 16 or the crystalline instruments, and of course, also the newest features of our software. Before we start, I would like to share with you that the webinar is being recorded and it will be made available to you after the webinar. In a few days, it will be available on our website and also on our YouTube channel. The same as the slides. If you'd like to rewatch them again, you can download them from our website. If you have questions, please write to us at info@crystallizationsystems.com. You are being muted. Therefore, questions can be written to us at this email address or to my email address, carmen.guguta@technobis.com, or the same to Jyoti, directly to Jyoti. She will also share her email address shortly, jyoti.yadav@technobis.com, and we will do our best to answer all your questions in a short time. Webinar will last about 30 to 40 minutes. Just before we start, for those who do not know Technobis Crystallization Systems, we are a company located in the Netherlands, in the north of the Netherlands. We are a Dutch company on the market since 2005, with more than 700 instruments installed worldwide, active in crystallization, process development, and formulation. A bit about our instruments. In our portfolio, we have three products: the crystalline, Crystal 16, and the Crystal Breeder. Some of you might know already the Crystal 16 or the crystalline, or even both. If after this webinar you would like to test one of our instruments, or you can either contact us directly via the website or send us an email at info@crystallizationsystems.com. Please remember, the Crystal 16 is your instrument for solubility metahistoic with determination, solid state screening, and the crystalline with the camera technology that works exactly like a microscope. You in situ, you can see what it's happening in the vial, and also Raman. If you have a Raman spectrometer, you can easily connect it to your crystalline, and you can follow polymorphic transformations or chemical reactions. Of course, you can optimize or develop your crystallization or formulation processes. The Crystal Breeder, the gadget type of instrument, how I'd like always to call it, with its controlled evaporation or vapor diffusion setup, is actually the ideal instrument that helps you growing single crystal or performing crystallization type of screens. Remember, Technobis is a provider for lab instruments, which enables you to measure, characterize, and control some of the properties related to crystallization, and I'm sure you'll hear more about this during this webinar. Our speaker today, as I mentioned to you, it might be that to some of you this face is familiar and you have already been in contact with her. Jyoti is our application specialist since mid this year. She was with us last year as doing an internship for 1 year. Now she actually finished her PhD, and soon, in a few weeks, she will defend her PhD on experimental investigation of the effect of solvent and ultrasonication on cooling crystallization of ascorbic acid at Indian Institute of Technology, Ropar in India. And now I would like to give the floor to Jyoti. You can start sharing your slides, Jyoti. Or shall I make you a presenter, actually? Yes?
Can I share now?
Yes.
I hope you can see my slides.
Yes, and now it's in slide mode. Perfect. Thank you very much, Jyoti, for bringing today this webinar to our attendees. The floor is yours.
Thank you, Carmen, for the introduction and, of course, for this opportunity to having me to speak. And good morning and good afternoon to some. As already introduced, I am Jyoti, application specialist from Technobase Crystallization Systems. And before joining as application specialist, I did a 1-year PhD internship at Technobase. And today in this webinar, I'm going to share some part of the study, which will focus on unlocking the power of solvent selection, influence on solubility, nucleation, and crystal habit of ascorbic acid. So during this webinar, first I will give a brief introduction about the compound ascorbic acid, and then the motivation behind this work, that is why solvent selection is important. Then coming to experiments, I will first share the experimental procedure to determine the solubility. Then before going to nucleation rate, I will discuss the basics of nucleation, which will include what is nucleation, different types of nucleation, and different methods to determine the nucleation kinetics. Then, of course, how to determine the nucleation rate from induction time measurement using Crystal 16 instrument. Then cooling crystallization experiment to see the effect of solvent and solvent composition on crystal habit. After that, we will come to results where we will see the effect of solvent system on solubility. Then how we can use the solubility data to predict the solubility in binary solvent systems using Joybin-Acre model. Then effect of solvent systems on nucleation rate and crystal habit. From crystal habit, we will see how crystalline instrument use the AI in predicting crystal shape, crystal size, and particle size distribution. And in the end, we will summarize this webinar with some conclusions. Ascorbic acid, commonly known as vitamin C, is an essential compound with a wide range of applications in pharmaceutical, food, health, and personal care industries. It has antioxidant properties, which is well known for preventing inflammatory diseases and boosting immunity. Now, solution crystallization is an important separation and purification step for the production of ascorbic acid, and water is used as a solvent for crystallization. But there are other solvents as well, like alcohols, which can be used for crystallization of ascorbic acid, from where the question arises, which solvent to select, or in general, why solvent selection is important. Because the solvent employed for crystallization controls the thermodynamic parameters like solubility, supersaturation, and solute-solvent interaction, then kinetic parameters like nucleation and growth rate kinetics, then final crystal attributes. The solvent employed for crystallization will control the final crystal attributes like crystal size, crystal shape, polymorph, and particle size distribution. Hence, the selection of appropriate solvent is an important part for the production of any API, and therefore, the focus of this research work is to study the effect of solvent and solvent composition on crystallization of ascorbic acid. Coming to experiments, first solubility experiments. To see the effect of solvent and solvent composition, 4 pure solvents were selected, water, and 3 alcohols, methanol, ethanol, and isopropanol. Then the binary solvent systems were prepared by adding alcohols to water, three binary solvent systems, water methanol, water ethanol, and water isopropanol. So these are the concentration of different binary solvent system in mole fraction calculated using this equation. Then to measure the solubility, 4 concentration of ascorbic acid were added in 1 ml of solvent system in HPLC vials. Then the solubility was determined using Crystal 16 instrument by polythermal method. Polythermal method is in which where temperature keeps on changing. So the instrument measures the change in the transmissivity, with the change in the temperature, which determines the clear and the cloud point. So clear point is defined as a temperature upon heating, where first 100% transmissivity is obtained, which indicates the complete dissolution of the solute. And cloud point is defined as the temperature upon cooling, where last 100% transmissivity is obtained, beyond which the transmissivity decreases, and which signals the appearance of the crystals. Then using clear and cloud point, you can determine the solubility curve and metastable zone width. And the difference between two represents the metastable zone width. Then these are the various operating parameters used: heating and cooling rate of 0.3 degrees Celsius per minute, temperature range between -10 degrees Celsius to 80 degrees Celsius, depending upon the boiling point and melting or freezing point of the solvent. We keep the solution few degrees below the boiling point of the solvent and few degrees above the freezing point of the solvent. Then the stirring speed of 600 RPM and the solvent volume for each solution was 1 ml. And coming to nucleation, so nucleation is the first step of crystallization in which phase transition occurs from supersaturated liquid phase to solid phase. And nucleation has significant influence on the next step, which is growth phase, and subsequently on the final crystal attributes like polymorph, crystal size, crystal shape, and particle size distribution. Now, nucleation can be categorized into two types: primary nucleation and secondary nucleation. Primary nucleation is formation of crystals in absence of its own kind of crystals, and it can be further categorized into homogeneous and heterogeneous nucleation. Homogeneous nucleation is formation of crystals in absence of any foreign particles, and whereas heterogeneous nucleation is formation of crystals in presence of foreign particles like dust particles, reactor wall, or stirrers, etc. Then secondary nucleation is formation of crystals in presence of its own kind of crystals, and there are various reasons for that, like collision, fluid shear, and seeding, which results in secondary nucleation. Now, nucleation is a stochastic process, and therefore it is difficult to know the actual mechanism for nucleation, but there are these two theories which explain or propose the mechanism for nucleation, that is classical nucleation theory and non-classical nucleation theory. According to classical nucleation theory, the molecules combine to form nucleus in one step. Whereas in non-classical nucleation theory, the nucleation occurs in two or more steps separated by free energy barriers known as pre-nucleation cluster. Here, crystal 16 uses, or we use, classical nucleation theory to represent the nucleation. Now the nucleation behavior of a solute in a particular solvent originates from the energy barrier for nucleation. So this is the energy change associated with primary nucleation. When the molecules combine, they form a cluster. And if the size of the cluster is more than the critical radius, this R critical, it forms nucleus, otherwise it's dissolved again. And nucleation can only happen if this energy barrier is overcome. Now, according to classical nucleation theory, the nucleation rate J depends upon the supersaturation ratio S according to this equation, where A is the kinetic parameter, which represents the number of active sites available for nucleation, and B is the thermodynamic parameter, which represents the activation energy required to nucleation to happen. Then there are two methods to determine the nucleation kinetic experimentally. First is polythermal method and second is isothermal method. The polythermal method relates the metastable zone width with cooling rates. You determine metastable zone width experimentally at different cooling rates. Then using different models, you can determine the nucleation kinetics or nucleation parameters. Whereas in isothermal method, it relates the induction time with the supersaturation ratio. The crystal 16 uses isothermal method to determine the nucleation kinetics or nucleation rate. To determine nucleation kinetic from isothermal method, more than 80 times or at least 80 times induction time is measured at 1 supersaturation. Then the probability to form a nucleus in a certain time frame can be described by Poisson's distribution, represented by this equation, where n is the number of nuclei formed in a certain time frame Tj within a volume V with a nucleation rate J. Then the probability to form one or more nuclei is 1 minus P naught, where P naught is the probability to form 0 nuclei. So the probability to form one or more nuclei is 1 minus probability to form 0 nuclei. If we substitute these values in this equation, we get this final equation, where Tj is the induction time, T is the time experimentally measured, and Tj is the growth time, which represents the time taken by the nucleus to grow into detectable size. And if we substitute these values in this equation, we get this equation. Then the probability is determined experimentally using this, where mt is the number of measurements in the certain time frame t, and m is the total number of measurement. For example, suppose here we have done 93 experiments at 1 supersaturation in water. So m will be 93. This is the total number of experiments, and mt is, we calculate probability corresponding to some induction time. Suppose we calculate probability corresponding to 10 minutes induction time. So the number of times the induction time was less than 10 minutes. Suppose here 30 times we observed experimentally the induction time was 10 minutes. So probability corresponding to 10 minutes induction time will be 30 upon 93. Similarly, we calculate for all the induction time the probability. And after plotting this probability, we curve fit using this equation using non-linear least square method. And by curve fitting this, we calculate the nucleation rate J and growth time Tj. And we do this for different supersaturation, at least 4 supersaturation. And after calculating nucleation rate J and growth time Tj at different supersaturation, and then using classical nucleation theory, which is plotted here, and from the plot, we calculate the induction time, we calculate the kinetic parameter A and the thermodynamic parameter B. So this everything is done by the Crystal 16 instrument, the latest version, where it used the automatic calculations to calculate these, to give these parameters. Then to perform the experiments for induction time measurement, you prepare 4 samples with different supersaturation, which is calculated using this equation, where Ci is the amount of concentration or concentration prepared by adding ascorbic acid in 1 ml solvent system, and Cs is the solubility at temperature where we want to keep our samples constant. For example, if we keep our temperature constant at 20 degrees Celsius, so it will be solubility at 20 degrees Celsius. After preparing 4 samples, we first heat at high temperature and maintain for some time so that every solute, everything is dissolved. And then we crash cool at a very fast cooling rate of 20 degrees Celsius per minute, which generates a specific supersaturation. And we maintain at that specific supersaturation for a long duration. And when the nucleation happens, the transmissivity decreases, represented by this cloud point, and the induction time is defined as the instance of creation of constant supersaturation and the instance of detection of crystals. We repeat these steps for more than 80 times at 1 supersaturation. Then these are the number of experiments performed. For the nucleation rate analysis, the different solvent system considered were water, with then the water ethanol solvent system with increasing concentration of ethanol 0.2, 0.4, and 0.6 in mole fraction, and then water and water isopropanol solvent system with increasing concentration of isopropanol 0.2, 0.4, and 0.6 in mole fraction. And these are the corresponding supersaturation for each solvent system and corresponding concentration and the number of data points collected for each supersaturation. Then coming to see the effect of solvent and solvent composition on crystal habits, cooling crystallization experiments were performed using crystalline instruments. For this, a predetermined amount of ascorbic acid as per solubility at 60 degrees Celsius was added in a 3 ml of solvent system in such vials. The program was first set to heat to high temperature 60 degrees Celsius, then cool at 220 degrees Celsius at cooling rate of 0.5 degrees Celsius per minute, and with the stirring of 600 RPM. During the experiments, the images were recorded at interval of 2 seconds. Then coming to results, these are the solubility curve for 3 different solvent systems determined using Crystal 16 experiments. It is noticeable that the solubility increases with increase in the temperature for all solvent systems. And this is the comparison of solubility in pure solvents with literature data. From this graph, it is evident that ascorbic acid has high solubility in water, followed by methanol, ethanol, and isopropanol, because ascorbic acid is a polar molecule, and therefore it has high solubility in high polar solvents like water, and followed by methanol, ethanol, and isopropanol. Now, at a fixed temperature, here you can see at a fixed temperature, the solubility decreases with increase in the alcohol concentration for all three solvent systems. This is again attributed to the fact that adding alcohol reduces the polarity to the intermediate values depending upon the concentration, leading to lower solubility in binary solvent systems. Now, from these graphs, we can determine the solubility at any temperature using these curves. But suppose if we want to determine the solubility at any temperature and at any solvent composition, for that, we have Joyben-Agre models. And this is the equation used for binary solvent systems, where XAA, this is the solubility of ascorbic acid in mole fraction, and X1, X2 represents the binary solvent composition, X1 as solvent 1 and X2 as composition of solvent 2. And this is the solubility of ascorbic acid in pure solvent 1, and this is the solubility of ascorbic acid in pure solvent 2. If we substitute this general equation, this our first equation, we get this as our final equation, where A1 to A7 are constant, which were calculated by curve fitting the solubility curves. And these are the obtained values of the constant. If we substitute these constant in this equation, we can surface plot the solubilities. And from these surface plots, we can determine the solubility of ascorbic acid at any temperature and at any composition of binary solvent systems. Now, coming to the nucleation rate, these probability plots are generated by Crystal 16 software using the equation and procedure as explained earlier in different solvent systems. Each curve represents one supersaturation. The probability curve first increases sharply and then flattens as it approaches to 1. At higher supersaturation, the induction time was less, which indicates that at higher supersaturation, crystals were formed quickly and easily. And from these curves, the nucleation rate J and growth time Tj were calculated by curve fitting. To see the effect of solvent system on nucleation rate, this is a comparison at one supersaturation. The nucleation rate J decreases with increase in alcohol composition. Here from pure water to increasing concentration of ethanol, the nucleation rate decreases, and the growth time increases with increase in the alcohol composition, similarly for water, ethanol, and water isopropanol solvent systems. Then further, the nucleation rate J is related to supersaturation ratio S according to this equation and are plotted in these graphs. And from the plots or from the graphs, the values of kinetic parameter A and thermodynamic parameter B were calculated from the intercept and the slope. The kinetic parameter A, which represents the number of active sites available for nucleation, decreases with increase in alcohol concentration in both water ethanol and water isopropanol solvent systems, whereas the thermodynamic parameter B, which represents the activation energy required for nucleation, increases with increase in alcohol concentration, which represents that higher activation energy is required to nucleate in water alcohol solvent systems. Then further using the thermodynamic parameter B, interfacial energy, critical radius, and critical Gibbs free energy were calculated using this equation from classical nucleation theory. And from here, we can see that with the increase in the supersaturation, the critical radius decreases. That means at higher supersaturation, nucleation with smaller radius are formed and requires less activation energy, which is represented by this critical Gibbs free energy. And from this table below, we can see that the effect of solvent systems on interfacial energy, critical radius, and critical Gibbs free energy. The interfacial energy increases with the addition of alcohol, which means or which reflects that interaction between the solute and solvent is difficult because of higher interfacial tension. The critical radius and the Gibbs free energy, as it is dependent upon interfacial tension, it also increases with increase in alcohol composition, which represents higher activation energy or higher driving force is required to nucleate in water alcohol solvent systems. Then coming to effect of solvent composition on crystal habits from cooling crystallization experiments, these are the images taken during cooling crystallization in different solvent systems. The effect of solvent composition on crystal habit can be seemingly noticed here. More cubic shaped crystals were formed in water, and with increase in alcohol concentration, more elongated crystals were formed, resulting in rod shaped crystal in pure methanol and in pure ethanol. Similarly, in water isopropanol solvent system, more elongated crystals were formed with increase in isopropanol concentration in binary solvent systems, and in pure isopropanol, cluster of needle-shaped crystals were formed. Although the crystal habit changed with different solvent system, but it has only one polymorph. The polymorphic study was not done with this research work, but you can find in this literature work. So the change in the crystal habit can be attributed to the change in the growth rate mechanism with the addition of alcohols. Rate of mass transfer decreases and the surface integration step increases, and therefore it results in growth in one crystallographic axis. Then from these images, we can see the effect of solvent and solvent composition by seeing the change in the crystal habit. But if you want to quantify or characterize in terms of different shapes and particle size distribution, for that, the latest version of crystalline instrument uses the AI. So AI is advanced technology which has the ability to detect particles that it has seen before. So crystalline first gathers a set of images where particles are clearly marked, and this collection of labeled images form the basis for teaching the AI to spot particles in new pictures. How does it work? First, the input. The process begins with providing the AI system with the images containing the particles. Then for processing, the artificial neural network or the brain uses the deep learning technology with learned patterns from the pre-processed images to analyze the input images. It looks for specific features or characteristics that indicates the presence of the particles. Then the particle separation will divide into different classification with matrix information. And after processing, the AI system provides an output that indicates the size and the shape of the detected particles. The particles are characterized into different shapes such as non-convex, quasi-equivalent, which is equal in all direction and it represents cubic shaped crystals, then needles, platelets, and spheres. And the particle size that are characterized are particle size, which represents the equivalent sphere diameter, contour parameter, contour area, ellipse shape factor, convex hull parameter, and convex hull area. Further, the AI systems gives information on particle size and particle size distribution in terms of D10, D50, and D90. This is the verification done with the glass beads of 10 microns size. Then the instrument uses the most recent development of AI to identify crystals automatically, and with this technology, a neural network is able to identify individual crystals pixel-wise. So the conclusion is state-of-the-art particle detection with identification and the ability to filter. So the AI detection will improve over time when more libraries become available. And with this, we will summarize our webinar. First, we saw the motivation behind this work. That is why solvent selection is important. Then we saw the solubility, how to perform the solubility experiments using Crystal 16 instrument, and we saw ascorbic acid has high solubility in water and decreases with increasing alcohol composition. Then we went through the basics of nucleation and discussed what is nucleation, different types of nucleation, and different methods to determine nucleation kinetics. And the effect of solvent composition on nucleation rate of ascorbic acid in various solvent systems, and saw that ascorbic acid has high nucleation rate in water. Then the thermodynamic parameter B, which represents the activation energy required for nucleation, increases, and the kinetic parameter, which represents the number of active sites available for nucleation, decreases with an increase in alcohol composition. The critical radius Gibbs free energy were determined from the thermodynamic parameter, and which increases with increase in alcohol composition. Then we saw the transformation of crystal habit with the solvent composition during cooling crystallization experiments. More cubic shaped crystals were formed in water, and with the addition of alcohols, more elongated crystals were formed. And then we also saw the role of AI, how crystalline instrument uses AI to detect particles in terms of particle size and particle shape. Then with this, I would like to thank you everyone for joining. If you have questions, please contact me at jyoti.yadav@technobis.com, and you can also mail at info@crystallization.com. And I would like to thank you, Carmen and Technobis, for giving me this opportunity and letting me share my research work. Thank you.
Thank you very much, Jyoti. Very nice webinar exemplifying the use of our instruments. I have a few questions and so for you. Because you have mentioned at one moment there were quite a few mathematical formulas that you have used there, and sometimes for some of us could be quite overwhelming, of course. Tell us a bit more about the software of the Crystal 16 in this case, but also the crystalline. Is it easy to calculate, for example, all these parameters, and is it an easy way to go from one step to another one?
Yes, what I can say is for the nucleation, specifically for nucleation analysis, the instrument, the latest version of Crystal 16 V3, it automatically generates these solubility, these probability plots, and from these probability plots, it automatically calculates these nucleation parameters, where we don't have to do anything or do the calculations. We only need to perform the experiments. And as I explained here how to perform the experiment, this is how we perform the experiments. Other calculations are done automatically by the Crystal 16 instrument. We just get the values of the nucleation parameters automatically. This is just to explain how Crystal 16 calculates the different parameters, just for us to understand the mathematics behind the calculations.
Mm-hmm. Okay, perfect. And if you go towards the crystalline?
Yes.
Those are some beautiful pictures. Yes.
Yes, for these as well, you can take the pictures with the crystalline instrument, and with the new crystalline, it will give you analysis on the different, like this is how it works in the background, but here also you don't have to do anything. It will directly give you the different shapes that it see in the picture and different particle size. And different parameters where it can give you. So here also you don't have to do anything. If you take the pictures and use the AI analysis, it will automatically characterize in different shapes with different colors and different parameters. And also it will give you the information of particle size and particle size distribution in terms of D10, D50 and D90. And you can select the time interval where you want to see these results or these particle size parameters. You select from the in the software, you select the interval when you start seeing your crystals. Then over the time, and also over the time, you can generate this particle size distribution. So you can determine then later the growth rate analysis with these informations.
Yeah, and the software comes with the multi-analysis software. So how it is called in the crystalline software package, with 3 possibilities of using either AI, either for particle detection, I mean AI, blob detection, or hybrid, a combination of the two of them. What we have seen during our experiments and also during the interaction with our beta customers from some time in the past, in some cases, depending on the shape of the crystal, the AI does a very good job. In other cases, the blob detection, and other cases as well, the combination of the two of them. So there's still not a straight guideline for, like, for example, needles, you should use these, for platelets, we should use this. I do believe we need more case studies to be able to draw such a line and a conclusion. But nevertheless, we already have started to see some trends. So you have this possibility in this multi-analysis package of the crystalline to use one or the other methods or the combination of them to be able to detect particles. And the added value of this software is that with the oldest way of image analysis or particle recognition, the biggest trouble would have been that if you have two overlapping particles, in most of the cases, and many software packages available out there, would have been seen like one big particle. The added value of using AI or the blob or the hybrid is that those two overlapping particles are history, let's say. So now you can really see that they are two different particles. Of course, also your calculations related to the, yes, indeed, to the particle size distribution are, of course, more accurate. Well, are accurate at this moment. So this is really something that brings this technology at the next level. Besides the cameras and the lighting, the front and back, that the technology is really improved on the crystalline, and now we can see much better in thick slurries or color sample, also because we also have color cameras, of course. Sorry for hijacking your your presentation, Jyoti. I just wanted to add this on the crystalline software. I think this is it from my side. Oh, and I have also heard you talking now, going back, sorry, to the Crystal 16. When you were talking about induction time measurements and all those cycles that you have mentioned, you have done it 80 times or so. I do recall the times when these methods were introduced, I think more or less in the same time, or now I do not know who was the first one, but I do remember that at MIT they did quite a lot of work on this, and they came up with this method published. The group of course, of Meyer, Professor Meyer, then also a group of Professor Job ter Horst, Professor Mazzotti, and after a few years, I think they also came back. Even Thomas Vetter, I do recall, he had a review, and most of them, they agreed that actually they determined a minimum adequate, optimal, let's say, number of cycle would be around 80 cycle, no matter the compound that you are using. So that's why I guess you have done the 80 cycles, right?
Yeah. It controls because nucleation is like a stochastic process. If you perform it a number of times, so it controls the stochastic behavior and it average out the induction time. So at least 80 times, so you can do more, but 80 times is like required number of repetition you need to do at one supersaturation.
To have reliable data.
Yes.
Yeah. And I do recall you have also mentioned to me, I don't know now if you mention it today, that in many cases you have performed experiments all 80 cycles in one type of run, but you can also combine from different runs, right? Can you say a bit more about this? Maybe you give an idea to our attendees today.
Yes, if in the software there is option you can perform the experiment continuously for 80 times, but also if you want to perform in multiple sets like 10 experiments or 20 experiments and then you want to combine it, that is also possible in the software. You use the multi-analysis option where you combine different experiments that you have run, and then also you can do the analysis for 80 experiments at the same time. And this is all mostly useful for compounds where it degrades after some cycles, especially when if you see some changes in the compound after a few cycles, 10 or 20 cycles. So in those compounds, you can perform the experiments in multiple cycles, 10 experiments or 20 or 30, and then you can take those experiments and combine in multiple analysis. So it will give you analysis for 80 experiments, or also at different supersaturation or at a different solvent compositions, that also you can combine in multi-analysis and see their plots in the same graph.
That's a good remark that indeed I didn't think about it. There are many compounds that they easily decompose chemically, so then you would like to still be able to have a good data set of reliable data, so then you can combine it in this way. That's a good one. I think this is it, Jyoti. Thank you very much. Thank you all for attending today's webinar. As I mentioned, the recording will be available on our website in a few days. You will also receive an email with a link towards this recording. Also to the slides where you can download them from our website. If you have further questions, do not hesitate to write to us at info@crystallizationsystem.com, to directly to Jyoti or to me. We will be more than happy to answer your questions. And I hope to see you to our next webinar. We are still planning one more webinar in the beginning of for the beginning of December, just before Christmas, to end up this year nicely. And hope to see you soon. Bye.
Thank you. Bye.